I need to share my screen. Can everybody see my screen? Yes, no?
Yeah, we can.
Hopefully. All right, cool. So today we're going to talk about the last part of this. Well, actually, there's another piece, but I'm going to push it because we still got to cover thermochemistry. We got to talk about electron configurations, Lewis structures. And I think what I'm going to do is just put lectures together on each one of those topics rather than just trying to go point by point from the book, because the book has it all, and I'll point you to where to look in the book or whatever, but I'm just going to put together a lecture for each topic. And that way you don't go into part 2 disarmed. You got everything you need for part 2. So let's today we're going to talk about, because we're still finishing up stoichiometry. So we're going to talk about what's today? The 6th. Yeah. So the last topic here with stoichiometry that we're going to be discussing is how to calculate like percent yield and theoretical yield and what they mean. And these are both very important concepts, especially percent yield. You're going to use that a lot in organic. When you get to organic, so it's really important to learn that now. And so we're going to talk about both. So percent yield and theoretical yield. So it's important when you think about a reaction. Let's say A plus B going to C. It's really rare that you have a reaction that goes to completion. Right, that's rare. It's rare that you get a reaction that actually goes to what we call completion, but that meaning all of your reactants react and give you 100% product. Right, that's rare. Some reactions you can get 99% yield, maybe 98% yield, but it's really rare to get a 100% yield. And there's a lot of reasons for that. Sometimes maybe it's the temperature is not high enough or low enough so that you don't get proper reactivity. Sometimes you could drop when you're weighing out, excuse me, your reactants. Something may drop on the bench top or drop on the side of the balance or something like that. And when that happens, then you lose a little bit of start material, so which in turn you're going to lose some product, right? And I know that it seemingly goes against the law of conservation of matter, right? You would think when you put these two things together, you should get 100%, but sometimes you have some operator error in the start material. We're going to call it operator error. Sometimes you get side products. Sometimes you get incomplete reactivity. In other words, the start materials react, but they don't necessarily react to completion. So there are a lot of different reasons why you don't get 100% yield. But every reaction has what we call a theoretical yield. So the theoretical yield is always in grams, right? That's important. It's always in grams, and it is the amount of product that you expect if the reaction goes to completion. So the amount of expected product from a reaction that goes to completion. It's what you expect. If you take A and B and you react them together and they all get consumed and do what they're supposed to do, then there's an amount that you can theorize and say, this is how much I should get, right? That amount, the theoretical yield, is always based on the limiting reactant. Right? The theoretical yield is based on the limiting reactant. You will not get any more product than the amount of limiting reactant allows, because remember, once the limiting reactant gets used up, then the reaction stops. Right? So the limiting reactant controls the amount of product that you get. Right? So it's based on that. So when we think about the limiting reactant and the theoretical yield being based on the limiting reactant, we also have to think about the fact that we can calculate the theoretical yield. But in order to do it, we're going back to the basics. We need a balanced chemical equation. And once we get that balanced equation, excuse me, once we get that balanced equation, then from that balanced equation, we can get the theoretical yield. All right, so I got some examples down here. So we're going to walk through about 3 examples. And then once we're done with these examples, we're actually going to stop. And then we'll pick up on tomorrow with some more examples. And then we're going to talk about titration. And on Friday, we'll start chapter 5. All right, so here we go. Here's an example here. You have this equation, which is already balanced. Potassium chlorate. And that is going to decompose to give you KCl, potassium chloride, and oxygen. And it's already balanced. So what are we looking for here? We don't have another reagent, so KClO3 is assumed to be limiting because there's not another reactant present. Right, so that we assume that to be limiting. Right, so look at the question. Potassium chlorate decomposes upon slight heating in the presence of a catalyst according to the reaction below. In a certain experiment, 40 grams of potassium chlorate, so it's giving us 40 grams of that to start with, is heated until it completely decomposes. What is the theoretical yield of oxygen gas? All right. So the theoretical yield we calculate just based on what we have. We have 40 grams of potassium chlorate. We have a balanced equation, and we have a way to go from grams to moles, because again, with the stoichiometry, we can figure out how much oxygen we're going to get from KClO3. What do we want to put in the top of our stoichiometric ratio? Which, if we're looking in terms of potassium chlorate and oxygen, what number is going to go in the top? If I'm trying to solve
3 moles of oxygen.
Yes, 3 moles of oxygen. So this is my ratio. 3 moles O2 over 2 moles KClO3. That's my stoichiometric ratio that I'm going to use to find out excuse me, how much oxygen I'm going to get from 40 grams of potassium chlorate. So we need to convert grams into moles. Is that right? Because we got 40 grams. We need this in moles because we can't use the stoichiometric ratio with any other unit other than moles. How are we going to do that? So we'll convert that to moles. Right? What do we need in order to do that? And if this sounds redundant or repetitive, it is, and it's repetitive on purpose, because the more you hear it, the more you touch it, the more you do it, it's going to stick. So I need to do what? Take what? Grams over molar mass to give me moles. All right, so what is the molar mass of potassium chlorate? Cl is 35, oxygen is 16 times 3, so that's going to be 48 and 35. What's that? 83. We just need potassium. Because we know this is
39.
48 grams per mole, because it's 16 times 3. This is 35 grams per mole. And you said, what did you say it was?
It's 39 grams per mole.
39 grams per mole. All right, so that's 83 and 39. What is that? 112 or 122? Is that right?
Yeah, I got 122.
All right, so we're going to take that 40 grams divided by 122 grams per mole to get moles. I need somebody to knock that calculation out. I don't have my calculator with me. It's going to be somewhere, that's about a third, somewhere 30 something, or 0.3 something, not 30 something, but 0.3
I got
something.
0.33.
So 0.33 moles. So we're starting out with 0.33 moles of potassium chlorate. Now we just need to set up the equation and use this to convert potassium chlorate into oxygen. Because remember, as long as we know the stoichiometry, we can turn any reagent into any product. We can figure out how much we're supposed to get. So we're going to do 3 moles of O2 over 2 moles of KClO3 times 0.33 moles of KClO3. So moles of KClO3 will cancel. What do we have? 0.45, something like that.
I got 0.495. So
All right. That's I'm just doing that off the dome. So yeah, I trust your calculator more than my brain.
I mean, you're doing pretty good. You're doing pretty good though.
0.495 moles. All right. So now let's keep in mind, this is in moles. The theoretical yield must be in grams. So I need to convert, this is of O2. So I need to convert moles of O2 into grams of O2. Right, so moles of O2 into grams of O2. And I know how to do this, right? I take the number of moles times the molar mass, right? So grams, moles times molar mass. And the molar mass of O2 is just 32 grams per mole. So that's going to be 0.495 moles times 32 grams. It's going to be close to 16 grams. Not quite 16, but close. Go ahead. Hit me with that.
I got 15.84 grams.
15.84 grams. All right, great, of O2. So theoretically, if all of that KClO3 decomposes we should get 15.8 grams. If we start with 40 grams, we should get 15.84 grams of oxygen gas. How much KCl should we get? Mass wise, think about it. I started with 40 of KClO3. It decomposes. It gives me roughly 16 grams of oxygen. How much KCl should be left over? Because in a mass, if the masses have to add up to the amount I started with, theoretically, how much KCl should be left over?
24.16.
Yeah, by 20. Yeah. So whatever the balance is of that 40 grams, it should be KCl if it goes to completion. All right. So that is 15.84 grams of oxygen. So let's see. So now that's my theoretical yield. That's my theoretical yield. It's 15.84 grams. That's if everything goes into, gets converted. Now, how do we calculate percent yield? Percent yield is different. Percent yield, that's why the theoretical yield has to be in grams. So the percent yield is the actual yield over the theoretical yield times 100, right? It's that simple. So it told us here that we collected 14.9 grams of oxygen. So the gas got weighed out. We got 14.9 grams. All right. So now for percent yield, we're going to put that 14.9, and the percent yield will never be more than 100. If you calculate percent yield and you get a number that's greater than 100, you've messed up somewhere. All right. So we're going to take the actual, which it gave us in the problem as 14.9 grams, over theoretical, which is, it gave us in the, which we just solved for at 15.84. Right, so you can see why it has to be in grams, so that can cancel, times 100. It's going to be close to 90. It's going to be 90 something, but not quite 100. What do you have? Anybody?
94.
So 94%. It's a very efficient reaction. If it's at 94% yield, that's excellent, right? So we have, again, in order to calculate the percent yield, we need to first find the theoretical yield. And we always base the theoretical yield on the limiting reactant, right? So the limiting reactant is going to control the amount of product that I get. When it runs out, that's the end of it, right? So if I have another reactant that's in excess, when I take the overall mass of everything, products and leftover reactants that included, right, they should equal up to, like if I started out with 100 grams of each reactant, and I have, let's say, one of the reactants only 50 grams of that reacted, right? And you get like 50 grams of product. So the total I started with is 200. If 50 grams of that start material reacted, and then I got 50 grams on the other side somehow, everything that's left should add up to 200. Products and leftover start materials included. That's what you call a mass balance. All right. Let's do another example. Any questions about this example? All right. Let's do another example here. It says use the the balanced equation below. It says if 40 grams of acetylene, which is this compound right here, and 65 grams of oxygen are used, so that's the oxygen, and 25 grams of water were produced, what is the percent yield? So we got 25 grams of water, but we don't know which one of these is limited. So when you have two reactants like that, you have to figure out which one is limiting, right? So the first thing we want to do is because the coefficients are misleading. Sometimes you can look at that and say, oh, it's 2 moles of acetylene, 5 moles of oxygen. That's very misleading. You got to find out, you got to go past that and figure out how much water would get produced from acetylene and then how much water would get produced from oxygen. So let's determine the limiting reactant. So we're going to figure that part out first. So we need first we need everything in moles. Right, we need everything in moles. All right, so let's do that. Let's take 40 grams of acetylene and convert that into moles. So that's going to be 40 grams divided by C2H2, that's 24, and 2, that is 26 grams per mole for acetylene for C2H2. And then for oxygen, it's just going to be, how much did they give us? 65 grams of oxygen over 32 grams per mole. All right, so and this is for oxygen. All right, can we get somebody to calculate the moles for each one of these? Oxygen one is going to be somewhere around 0.5 or somewhere like that.
For acetylene, I got 1.54.
Okay. And how much for oxygen? Should be like not 0.5, be 2 point something or 1.9 something.
I got 2.03.
So 2.03 moles of O2, and this is C2H2. All right, everybody following so far? So we can't determine the limiting reactant until we first get all of our numbers, given numbers in moles. And that's because we're going to use the stoichiometric coefficients and the product, the desired product. We're going to use those to figure out how much product we're going to get. So let's start with acetylene. So we're going to see which one of these gives us. And remember, when we're looking for limiting reactant, what we're looking for is which one of these 2 star materials is going to give us the least amount of product, the least amount. So let's figure that out. What's my relationship between acetylene and water? What's the stoichiometric relationship between those 2?
2 to 5.
Acetylene is
2 to 2.
2 to 2 or 1 to 1, right? So we're going to say for acetylene, and I'm putting water in the top. 1 mole of water over 1 mole C2H2, right? We know from the equation that it's 2 to 2, but you can reduce that down if both numbers are the same. And then I'm going to multiply this by the moles of acetylene we calculated up top. So 1.54 moles of C2H2, because I want to cancel that. So that's going to cancel, right? obviously is going to be the same number, but water and not C2H2. All right. 1.54 moles of water. That's how much water acetylene is going to give me. Now let's see how much water oxygen gives, right? So we'll say that what's the relationship between those two?
Five to two.
5 to 2 or 2 to 5, because I want to put water in the top. So it's going to be 2 moles of water. I'm sorry, yeah. 2 moles of water over 5 moles of O2. And I'm going to multiply that by 2.03 moles of O2. All right. And that's why you have to do it this way. It's very misleading to just look at the coefficients and assume that because one number is bigger than the other one, that that's going to be limited. Sometimes that's the case, but not all the time. So you want to be thorough with this. So what do we get here? 4.06 divided by 5. It's going to be a smaller number than 1.54. Anybody got it yet?
I got 0.812.
All right, so 0. What we're saying is the theoretical yield of water, because that's what this is. When you take in the reagents and you figure out how much product you're going to get, these are actually theoretical yields, but they're in moles. We have to convert them into grams. So I'm just going to put that here. All right, so these are actually our theoretical yields. So we see that with acetylene, the theoretical yield that's of water based on that is 1.54 moles, and we can convert that into grams. And with oxygen, the theoretical yield is 0.812 moles, which we can convert into grams. But which one is less? If we're comparing the molar amounts, oxygen is limited. Is that right? Because it gives us the least amount of product. All right, so we're going to put that, say that oxygen now, would you have predicted that based on those coefficients? If that's all we used?
No.
No. You say, oh, you got 5 moles of oxygen, so that must be excess. And acetylene has to be limited. That's why you have to go through the process. Everything has to go through this process if you're trying to figure out what your limiting reactant is. All right. So now we know that's limiting. So we know what the theoretical yield is. We just need to convert that into grams. Since that's limiting, you can convert that amount into grams. To find a theoretical yield. Because that's always going to be based on your limiting reactant. So the theoretical yield is, what is that, 0.812 moles times 18 grams per mole, because that's the mass, that's the molar mass of my product. So 10% is 1.8 times 8. What do we get from that? About 15 point something.
Wait, we just multiplying those two numbers, right?
0.812 times 8.
Okay.
Times
I got 14.61.
14.61. Okay. It's 14.61 grams. All
Well,
right.
0.62.
Anybody not following this? 0.62.
Yeah, once you round.
So that's my theoretical yield. Again, I'm basing that on a limited reagent or limited reactant. And then it told us up top that we got 25 grams of water that was actually made. So this is the theoretical yield. And now we can take that number and find the percent. I don't know why this is dragging like this. It's going to be actual this is not going to turn out the right way. Oh no, let me take that back. No. Yeah, that actual yield is too high. So we're gonna chop this down and say it's 15. Actually, we're gonna chop it down even further. Because if it's 25 grams actual, then that something is off. We're gonna say it's 10 G's. So it's gonna be 10 grams divided by 14.62 grams times 100. What do we get for that number there?
68.4%.
68.4%. All right, so but do y'all understand why that 25 we couldn't use that as the actual yield? That would be over 100%. If the theoretical is 14 grams and it's telling us we made 25 grams, something ain't right. So I think whoever wrote this problem, they either wrote it in as a trick to say that we had to do something different, or they just made a mistake, an honest mistake, which happens. All right, but the process though, let's focus on that. We had first to determine the limiting reactant. Second, figure out the figure out the number of moles of each one. First, turn everything into moles. Then use the ratios from the equation, balanced equation, to determine the limiting reactant. And then that limiting reactant is also what we use to get our theoretical yield, which we said was 14.62 grams. And then once we did that, we can take the actual, which changed it from 25 to 10, so it would make sense. And then the theoretical was 14.62, and then we got 68.4%. All right, any questions about that? All right, I want to see if we can work through this one. I want to see if somebody can walk me through it, or multiple people can walk us through this last one. Just water on the screen or something. Just not acting right. All right, so let's look at it. It says if 100 grams of CO, just telling us how much we're starting with, reacts with an excess of H2 to form 75 grams of CH3OH, what is the percent yield? All right, what did it just give us? What did it just tell us that in this problem, what is it telling us about the relationship between CO and H2? What is it telling us?
That CO is the limiting reagent.
See, thank you. That's excellent. CO is limited. If H2 is in excess, the other reagent by default has to be limited. So what do I need to do to find the percent yield for this problem? And this is the equation right here. What do I need to do? If I know the limiting reagent off the break, how do I find the theoretical yield? All right, wouldn't I take this, convert it into moles? That's the first thing I'm gonna have to do. And then I'm gonna convert moles of CO into moles of methanol. All right, that's going to give me my theoretical yield in moles. Then I need to convert that into grams. So I'm going to convert the start material, the limited, what they gave us, into moles. Convert moles of CO into moles of methanol. Convert moles of this into grams. Is that right? And this is going to give me my theoretical yield. And then it gave me the amount, 75 grams, as the actual yield. Right? So I'll leave this open-ended until tomorrow. Somebody can come in and present that to us tomorrow. Just, it doesn't matter who it is. You have everything you need. If you got a periodic table, you got everything you need, because you can figure out molecular weight, and that's a huge part of the equation, going from grams to moles. You need molecular weight. All right, we're gonna stop right here. Any questions before we stop? All right. Let me go back to Zoom and stop sharing and stop recording.